Hello everyone, welcome to a new episode of Golan Cafe. Today we are going to go through Advent of Code Day 7. Advent of Code is a series of programming puzzles for who doesn't know what Advent of Code is, and each year we're gonna have 25 days of puzzles, 25 puzzles, and each puzzle has two sets. So it's the same problem, just slightly different problem statements and outcomes for the two sets. Today's problem is quite interesting. It's interesting because we are going to go through a graph problem, and we are going to go through DFS, which is depth first search. We're going to attempt implementing this in this problem in order to solve the problem statement here. So this is about language processing, and let's just go through very quickly the problem statement so we can understand what we need to do in this problem here. Due to recent aviation regulations, many rules, which is the puzzle input, are being enforced about bags and their contents. Bags must be color-coded and must contain specific quantities of other color-coded bags. For example, consider the following rules, and you will see here you have a list of rules. So each line is a specific rule. Each bag has a specific color code and can contain 0 or more other bags. And here you will see that we have light red bags contain 1 bright white bag, 2 muted yellow bags, dark orange bag contain 3 bright white bags, 4 muted yellow bags, and so on and so forth until you reach the end of the lines, the end of the puzzle input, which is the rules. So here you have a bag, and that can contain 0 or more other bags, as we can see in our example. These rules specify the required contents for 9 bag types. In this example, every faded blue bag is empty, every vibrant plum bag contains 11 bags, 5 faded blue, 6 dotted bag, black, and so on. You have a shiny gold bag. If you wanted to carry it in at least one other bag, how many different bag colors would be valid for the outermost bag? So the problem itself is how many colors can eventually contain at least one shiny gold bag. And here it goes through the rules. It just defines and trying to explain better how we can arrive at the end of this problem. It says, a bright white bag, which can hold your shiny gold bag directly, which is one color, which can contain the gold bag. The muted yellow can also contain the shiny gold bag, so it's 2. Dark orange bag, which can contain old bright white and muted yellow, so it's 3, which is dark orange. And then the fourth bag type that can eventually contain the shiny gold bag is light red, because we need to, so it's 4 in total, as you can see here. So we need to take into account that those bags can contain each other, and we have some kind of tree structure, if you will. So that the light red bag contains one bright white bag, and the bright white contains a shiny gold. So it's kind of a tree structure where you have a set of bags that contain each other, and we have the shiny gold, which is the bag we want to figure out. We want to figure out how many bags can contain this shiny gold bag. We can do that by using a graph. So we see that this is the structure of the problem is very resembles the structure of a graph, and specifically the type of graph that we're gonna see today is the directed acyclic graph. Directed acyclic graph because each bag represents a node, and each bag can contain certain bags, but this doesn't apply the other way around. For example, if a shiny gold bag contains a light red bag, doesn't necessarily mean the light red bag contains a shiny gold bag in itself. So that's why it's directed. So it's directed acyclic graph. Acyclic, we assume that there is no cycle. So if there were to be any cycle, then would be impossible to count almost impossible to count the number of parents in a node in that case. So for us it's fairly easy because we don't have cycles, we have direction, so it's kind of a directed acyclic graph. And the algorithm that we can use to count all the bags that can contain eventually a shiny gold bag is the depth first search. So we can just start with the shiny gold bag and then find out all the parents of the shiny gold bag using DFS until we reach the end of the graph, basically. So we can just see all the parents of the shiny gold bag. For each of those parents we see the parents of the parents, and for each of the parents we see the parents of the parents on the parents until we reach the end of the graph, basically. then that's just a DFS. And that's eventually what we need to do. We need to implement a DFS in this case, and the DFS is going to use the parents to explore the graph, and the graph is directed at a cyclic graph, so we know already the structure of this graph. The problem is, I think in this case the programming puzzle is in two parts. The first part is parsing the structure of the input and converting that into a structure that can be then represented as a chart, as a graph. And then afterwards is the implementation of the DFS, which we can do today very quickly, and then in another episode we can actually go through the details of the DFS and see better the algorithm itself. So the first thing that we are going to do is to get the puzzle input. So the puzzle input, as you can see, is quite large, and we are going to now create input.txt, and we are gonna paste all the puzzle input in our file. And now we are going to create our usual file where we do all our operations. So we use io-util read file as always, input.txt. We check if there is any error in this case, which it shouldn't be, but just the usual routine. So now we need to define the structure for our graph. The structure for the graph, in this case, we're just going to define a node in the graph, and we call this node bug. We use a struct. The bug for sure has a name, so we have a name, which is the identifier for the bug. You have to think of it as an ID. And then we have the children of the bug. The children is a slice of bugs itself, and we also want to have a parents field, so that we can easily go visit the children, and we can easily go and visit the parents. So obviously the first step is going to be creating the bugs and creating the children, which is in our input file. And then we need to go through another step, which is constructing the parents for all our nodes. In the case of graphs, at least specifically now for this case, what I want to do, I want to have a lookup table where we are going to store all the nodes, and the lookup table is going to be called bugs, and I'm going to use a map from string to pointer to bug. And this is going to be our lookup table, so our graph, in a way that we can easily access all the nodes. As always, we are going to parse line by line using byte.split, and then we are going to parse obviously by new line here, and we are going now to have to parse the actual bug. So how are we gonna parse the bug here? So we know that we have the contain key, the contain name, which is going to be the bugs contain name, which is going to be our string of reference, and then we can split the line using this string of reference. And we know that on the left hand side we're going to have our bug name, on the right hand side we're going to have the children of that bug name. So we have parts which is equal to string.split, strings.split, and strings.split is string.line because it's a byte slice, and we are going to use bugs contain. Now what we're gonna do is create parent, which is bug, pointer to bug with the name of parts of 0, sorry. So we have here the line. We split the line by bugs contain string. So on the left hand side you have the parent name, and on the right hand side you have something else. You have all the children. How are we going to parse all the children? We are going to split the children by comma. We know that this is something that appears for each child. Some other cases you don't have any child, so it doesn't matter because we still save the parent. But for when we have the children, we can just split by comma here. So now what we're going to do is just going to be splitting by comma. Child range strings.split. We split the parts.1, which is the right hand side of our string, by comma, and we go through all of this now. So we have a child for each of the parent, children for each of the parent here, for each iteration. How are we gonna parse the children information? So we need to parse the number. For now, the number is not used. It's going to be used in the second problem set. So we are still going to attempt to parse the number and put it aside. But the important thing is we need to parse the name of the children here. And you see the name is between an integer, a space, then you have the actual name, then you have another space, then you have bug or bugs, depending on whether they are more than one. I think this is a specific, this is a very simple case on when we can, clear case on when we can use the regular expression. Regex must compile. And the way we are going to define that is we are going first to define the integer value that we want to parse, which represents the number of bugs. Then we have a space, a literal space for our bug. Then we have another capturing group, which is A to Z value, and then it also can contain a space. We add the modifier that means that modifier means this pattern here, A to Z, and the space can be repeated one or more times. Then we have the space. So we capture the number, we also have a space, then we have our bug name, which is the second capturing group, then we have a space, and then we have bug or bugs with S. So we need to add bug literally, so if you just put bug, it just will match bug literally. Then we have the S, which can compare 0 or more times. And then we have also for the last, for when we are at the last step, at the last child in the list, we can also have a dot, which is optional. So to add optionality, as we've seen, we just use this pattern here, and we use the star sign, which means this repeats 0 or more times, as we've done with the S as well. So this should help us match our bug. So the matches are going to do child regex. Find string submatch, and we are going to match the child if the len of matches is less than 3, and is less than 3 because we have two capturing groups. So we have the first capturing groups, which contains the number of bugs. We have the second capturing group that contains the bug name, and the first one before these two is the string regex itself, which is going to be contained inside the matches array. So we should have at least 3. If we don't have 3, it means that this is not matched, which is in the case of, for example, when we have when we have no other bugs. We won't go inside this loop at all. So this is all just to make sure that we don't have any issue around the parsing of the bugs there. So now we know that we have the bug name, the children bug name, the children how many times that child bug appears, and we can also parse that. We can just put it aside for now. We know that this is matches of 1. Matches of 0, remember, it is the regex is the whole string that gets matched, so it's the whole string. Matches of 1 is the first capturing group, which is between the round parentheses. Matches of 2 is the second capturing group, which is the round parentheses here. So now we're going to use the second capturing group, which is child bug. Child bug is going to be bug, name, and matches of 2. And then what we are going to do is parent.children is equal to append parent.children our child bug, okay, child bug. So this is our parsing of the children, appending them into the parents. The next step, once we have parsed the parent, we have parsed all the children, we just go into our lookup table and we say bugs of parent.name equal parent. So now we can quickly access all the top level, all the root nodes in our graph, basically. And this should, I think, should also give us a representation of the bugs that we have parsed so far. So we can just go imports and print the result and trying to run the file and see what's happening here so far. Line 26, parse of 1. As always, we need to check if the line is empty, because the last line is always empty here. Continue, so that we don't get in the way with this error. And here you see that you have already parsed. We have already parsed all the bugs. Now there is a slightly small issue, because we have parsed all the parent bugs, so the root bugs, and we have the children there. We just miss a part of the structure in our chart, in our graph, because we have populated all the children for all our bugs. We also need to populate all the parents, because we need to walk, remember, we need to walk on the parents, using the parents. We need to walk up the graph until we reach the end of the graph and use walk up using the parents. So the first step, as we said, is parse the input into graph structure. The second step is build. Actually, it's not actually build. Is add the parents to the nodes, and we're just going to use the bugs variable that we have used. So we're just going to go through all the root nodes. We are going to go through the all the children here. So here we have range of value.children. We're going to go through all the children, and then we are going to basically for the bug that we are in here, which is bugs of k or v, that one is going to be basically added into the parents of each of those children, because we basically populating the parents field of each node. And to populate the parents field of each node, we go into each node, we get the children, and for each children we append the parent into that node, basically. So we just need to populate the parents field. The first thing we need to do is get the child, and I want to get the childs from the main structure, so we make sure that we don't create new nodes and we get lost in the way. We need to get the child in the bugs lookup table, because you want to always work with the same data. And how do we get the bugs from the lookup table? We need to use the name of the children, children idx.name, and this is okay. If not okay, then there is some problem. We assume that we have all the nodes in the parent lookup table. Not found. So we get from the bugs, we get the children name, the child name, and here so the bugs.v.children.name is actually bugs of k, and children, actually this is k is the bug name, and the children name is v.children.idx.name, because we are trying to attempt to get the child at position idx for a position idx, and that child has a name, and that node is already something that we already know. We already got this node from the original parsing. That's what we want to get as a child. And once we have this child, we do child.parents equal to append child.parents. And what we're going to use as child.parent is going to be the parent of these children here, which is bugs of k of v directly. So it's bugs of k. This is the parents. And then once you have done that, what we want to do bugs.k.children.idx equal child, because we want to make sure that we update the value, so we don't lose the value of parents. Child.parents is not not something that we're going to lose after this operation. So we go into the node we are at, we get the children, we go into the indexes of the children, the child we are at, and we override the child, which contains now the list of parents updated. and actually I want to remove the v here. And the reason why I want to remove the v and I'm using all the indices is because you want to make sure that you're not working with a copy of the node, you're working with the actual node, with the pointer to the original node. And because when you have the v here, it's just a copy. It's not the actual value that you want to use. So if you change the copy, if you use the copy, you change the copy, then you lose the value at the end of the iteration. So you want to make sure that you actually use the node that you want to update. So now we should have all the parents in place, and now is the turn to implement the DFS, which is depth first search. The depth first search we're going to see in the next episode, but it's basically composed of a couple of components. There is a next array, which in our case is the array of nodes that we need to visit, and the array of nodes that we need to visit for the beginning is just one, start, and the start is effectively just the shiny gold bug basically. So we start with shiny gold bug, we add it to the array of next item to visit. We also want to keep track of which item we have visited, and that is going to be a set. Remember that in Go the set, we don't have a native way to implement the set, so we're just going to use a map with a struct value there, which we're not going to use, we're just going to use the keys. And then until we have item inside next, we do the following. We get the first item in the next array, so we treat next as a stack, so we pop an item from the array, so which is next of 0. Then next is going to be reduced, so we are going to remove that item that we just taken from the array by slicing next from item of 1 until the end of next. So we basically just remove the first array here, the first item here. And then what we're going to do, we're going to go through the parents, so range of end of parents. That's why we needed to do all the work there to load the parents. So range over the parents, and then what we're going to do is next equal to append next, and then v, which is the parent of that node. And then we want to update visited with end.name, and we are just going to add the struct here. So now if you tell me the shiny gold bugs, how many parents does the shiny gold bugs have? Well, the number of parents of the shiny gold bug is equal to the length of visited minus 1, because visited also contains shiny gold bug. So it's going to be equal to visited minus 1, the length of visited minus 1. And this is true because once we start with shiny gold bug, then we get shiny gold bug here n, next is empty, then shiny gold bugs.parents contain all the parents that we are expecting to find that contain shiny gold bugs itself, and we append those nodes inside next. We mark shiny gold bugs as visited. We go again. We like if we could recursively call this function here. There is also a recursive version of this, but I think this is even clearer to understand. We go through next again until there is no more parents to visit, basically, because we go through next again, we pop an item, we check all the parents, we append the parents to next, and so on and so forth, and we check all the parents until there is no more parents to go through, basically. And since this problem doesn't have any cycle, we are good to go in this way. Otherwise, we would have also had to check if we had visited. So if we have visited end.name, then we would have skipped that item, because you would end up in an infinite loop in this case. If there is always a parent to a node, then this loop never ends. So now the final result is log.println, which is len of visited minus 1. Remember, because visited also contains the initial node, which is the shiny gold, which we don't want to count. So let's go imports here, 44. Actually here we need v.children, just to use, we can also use this notation here, also 45 probably. So 45, which is the same. You could also leave it as a v, but that was just an example for you to make sure that we are not using any copy of the node, because it can be quite confusing and quite error prone, because sometimes you're using the copy of the node, you're trying to update the copy, but then that doesn't get reflected into what you are actually, into what you want to actually do there. So let's see what's the issue here. Next, dot parents append next v. I'm not sure if where the issue is in this example here. So we know that the bug arrives here. Bugs okay that children. There must be some issue with the DFS. Next, 0, 1. Here we don't want to redefine next as 119. So the error here is that we were defining next from scratch, so we just need to override next. We don't have to redefine it from scratch. And this gives us 119, which is the expected result here. So the number of how many bug colors can eventually contain at least one shiny gold bug, the answer is 119, and that's because that's exactly saying the same as saying as how many parents does the shiny gold bug eventually have. Like if you walk up the tree and use always the parent, you can use a DFS to count how many different bug types you have. Part 2 is slightly different. So it's getting very expensive to fly these days, not because of ticket prices, but because of the ridiculous number of bugs you need to buy. Consider again your shiny gold bug and the rules from the above example. And here now it goes and it mentions the number of bugs, because up until now we have not dealt with the number of bugs. We just said this is the types of bugs that you can the certain bug can contain, but we are not use this multiplier here, which is how many of those type of bugs a certain bug can contain. And here it goes and it says all the different type of bugs and also the multiples of how many this type of bugs can be contained into another one. So a single shiny bug must contain one dark olive bug and the 7 bugs within it, plus 2 variant plum bugs and the 11 bugs within each of those. And so you have 1, which is dark olive, 1 multiplied by 7, which is dark olive multiplied by 7 contained within dark olive, 2, which is 2 vibrant plum bugs, plus 2 multiplied by 11, which is 32 bugs. Of course, the actual rules have small chances of going several levels deeper than this example. Be sure to count all the bugs. Okay, so we now have to do, the question is how many individual bugs are required inside your single shiny gold bug. So now the question is slightly different. Instead of counting the parents, we need to count all the children, and for each child we need to take into account how many times that bug appears as a child inside the parent. And this is something that we already have in our problem. So if we just copy our 1.go into 2.go and we go into 2.go, this time we already have the times here. We just need to properly parse it, and is string conv ASCII to integer, and if there is any error we continue, and then times. Then what happens here is that we are going to go through, we are going to append a bug as many times as we see it in time, as many times as we see it in our rule set. So we're going to use a for loop, and then we are going to add it there. So we append the child into the parent as many times as we see, as we have defined by the rule here that we have parsed in our regular expression. Now, from the shiny gold, instead of looking up the parents, we need to look up the children there. So we can just go here and do children, and for each child, then we just need to count the total number of children that we see here. So now instead of visited, we just need a total counter that starts from 0, and then at the end we can just print the total counter here. And I think this should do. We also need to import string conv and to.go. And this is 155,802, and this is exactly the expected output in our problem. So the problem of today, if there is something you can take away from today's problem, is the graph structure. This is a directed acyclic graph. There are no cycles in the graph because, as you can see, this is an assumption that I've made, and it's correct in this case. So we don't have any cycles. So there is no bug that contain another bug, and there is an infinite loop inside the graph. So it's a directed acyclic graph. It's directed because the rules are one way from a bug to the other. The bug represents a node, and the problem can be easily solved by just using a DFS algorithm. And the DFS algorithm can be used to walk up the tree in different directions. So the direction towards the parents in the first example, so you just can use the parents, and the direction towards the children in the second example. And that's also another case of DFS. In another video, we're going to explore with more in depth. We're going to explore the DFS algorithm. We're going to explore more graph problems. And if you're interested in that, just let me know in the comments below, and we can go through that as well, more in depth. But that was today's problem. It was quite interesting. I hope you liked it. Thank you. See you in the next one.